Welcome back to the lecture on kinematics. Before we start, let us refresh what we have learned so far. We started the lecture by exploring the word kinematics, and we understood that kinematics is the study of motion with no regards to the forces causing the motion. And we took an example of me at certain time t equals to 0. I'm at this position. At certain time t equals to t, I reach a location here. And we explored there are 4 quantities or parameters that can fully define the kinematics of any body in motion. And time is definitely one of the quantity, followed by displacement s. Displacement s will provide the distance as well as the direction of motion. And the rate of change of displacement is given by the velocity. And the rate of change of velocity will be given by the acceleration of the body. So these are the 4 key parameters or quantities that we learn that can define the kinematics of a body in motion. And thereafter we moved on to another important aspect of kinematics, which we call the VT graph. As the name implies, it refers to the velocity time graph. This graph along the y-axis, it contains the velocity information, and along the x-axis, it contains the time information. And we gave you an illustration or example of a SMRT train traveling from Dover to Clementi Station. And as you can see, this is a typical vehicle kinematics profile. It accelerates from stationary position, maintain a constant speed where acceleration is 0, and just before it reaches its destination, it decelerates to a complete stop. So again, a VT graph contains all the 4 key parameters: the time, velocity, acceleration, and last but not least, the displacement, which can be found with the area under the graph. After learning about the VT graph, you'll be introduced with the 4 kinematics formula, which the first 2 formulas form the basis for the derivation of the third and the fourth formula as illustrated during the lecture. Please do note, these kinematics formulas are applied in stages. For example, in this example of a kinematics VT graph of a moving train, these 4 formulas are applied at the stages as illustrated. This is stage 1 of the motion where the train is accelerating. When A is 0, stage 2, and stage 3. Please keep in mind the formulas are to be applied at the various respective stages of motion. So far we have analyzed linear motion along the x-axis. So what about motion in the vertical y-axis? Now, for the vertical linear motion, in this chapter, we will only deal with free falling bodies, meaning that the body is only subjected by gravity, and we assume the acceleration is uniform. And you'll be glad to know that the analysis for vertical linear motion is exactly the same as horizontal linear motion, with the same set of formulas to be applied. But there are 2 differences compared to the horizontal linear motion, and it all lies with the acceleration A. Let me illustrate these 2 differences in the acceleration. Let us look at an example of a ball being thrown upwards. Now, during the upward stage of motion, the ball travels from my hand up, and you will reach to a certain height where the velocity turns to 0, and that's where the ball starts to travel down back to where I threw the ball. Again, as I mentioned, the differences between the linear horizontal motion compared to the vertical lies in the acceleration A. So the first difference will be the value of A for vertical motion. The value of A for vertical motion, we assume that it is uniform and is always equal to 9.81 meter per second square. So that's the first difference. The second lies in the sign convention for this A. The upwards direction is considered as negative and the downwards is considered to be positive. Again, you need not memorize this information, but rather you need to understand why. So basically, there are two stages: the upward direction, which is the first stage, and the downwards. Let us consider the upward, which is the stage 1. Now, for stage 1, we know that the ball travels upwards and it needs to leave my hand with a certain velocity. So the V0 for stage 1, I need to provide it with a certain velocity V. And as it travels up, it will reach to a certain height whereby the final velocity will be 0 meter per second. Now, let us analyze the upwards direction. Acceleration is equals to final velocity minus initial velocity divided by time. Now, take a look at this. Based on this stage of motion, what is the final velocity? Obviously is 0. Initial is v along with time. So we get a negative v over t, which implies that the acceleration is negative. Now let's take a look at the downward direction, which is stage 2. Now, as I mentioned, for stage 2, the initial velocity is 0 meter per second. And due to gravity, it accelerates downwards and will reach back to the original spot where it's been thrown with a certain velocity v. So in the same spirit, let us analyze the downward direction. We will have A, same thing, final velocity minus initial divided by t. Final velocity this time is v minus initial 0 divided by the time. And there we have it. We have a positive A. So this is the second difference as compared to the horizontal motion. A is considered positive when it's traveling downwards and negative when it's traveling upwards. So we have covered horizontal linear motion, and today we extend it along the vertical direction. And again, both shares the same set of kinematics formulas. The difference lies with the parameter acceleration A. And the differences are: A for linear vertical motion is taken as 9.81 meter per second square. And the sign convention, when a body travels upwards, which is against gravity, A is taken as negative. And when the body is free falling due to gravity, A is taken as positive. So for that, let us take a look at further examples that put all these theories that we have learned into context.